I would like to find the angle between the diagonal of a cube and one of its edges. So for convenience, let's consider the unit cube positioned on the first octant so that the back left corner is at the origin and its edges lie along the coordinate axis. Let me try to graph it for you. Okay, so this is the unit cube on the first octant, and this is the origin. I want to find the angle between this diagonal and, for example, this edge. I'm looking for this angle. Okay, so let's consider using the vectors. I have one vector. The diagonal vector is from the origin 0, 0, 0 to the point 1, 1, 1. Okay, so this is one vector, and let me call it u. So the vector u, if I want to write the coordinates of this vector, would be 1, 1, 1 minus 0, 0, 0, which would be 1, 1, and 1. Okay, and the other vector would be on the x-axis 0, 0, 0, beginning at the origin, and the point 1, 0, 0. Okay, let me call it v. So the vector v is the end point minus the beginning point would be 1, 0, 0. Okay, now I want to find the angle between these two. Let me give you a recall of the formula. So a recall. If we have two vectors a and b, and theta is the angle between them, a dot b is the length of a, length of b, and the cosine theta. So cosine theta would be a dot b over the length of a times the length of b. Great. So the cosine of theta here, this on the example, it would be u dot v over the length of u, the length of v. So it would be 1, 1, 1 times 1, 0, 0 over the length of 1, 1, 1, which would be 1 square plus 1 square plus 1 square times the length of 1, 0, 0, which would be 1 square, 0 square, 0 square. So on the numerator, I just have 1. On the denominator, I have root 3 times root 1. So the cosine of theta would be 1 over root 3. So theta would be arc cosine of 1 over root 3, which is approximately 55 degrees. Show that the vector b minus projection of b over a is orthogonal to a. This vector in here, we call it b over a, orthogonal projection of b over a. Okay, so let's see what we have. We have a vector a, we have another vector b, and we found the projection of b over a. So projection would be here. I need to find b minus projection of b over a. So b minus the green vector I need to find. So let me graph the negative of the projection. So this is the negative projection, and I'm going to move it to the end of the vector b. Okay, so let me erase this too. Okay, so as you see, this vector in here would be b minus projection, right? I can move this blue vector to go here. And so this vector in here is orthogonal projection of B. Great. Then I need to show that this blue vector is actually orthogonal to A. Okay, how do I do that? Let me give you a recall. If we have two vectors u and v, then u dot v is length of u, length of v, and cosine of theta, the angle between these two. So if u and v are orthogonal to each other, I keep writing v, I don't know why. So if u and v are orthogonal to each other, then cosine of theta, theta in that case would be pi over 2, cosine of that would be 0, so u dot v would be 0. Okay, so to show that this blue vector orthogonal projection is perpendicular to A, is orthogonal to A, all I need to do is to find the dot product and show that the dot product is 0. So let me write this. I'm gonna have orthogonal projection of B dot A, and I need to show that this is 0. So it would be B. I'm gonna replace definition of orthogonal projection of B over A and the dot product with A. So I'm gonna distribute A to this summation of vectors. It would be B dot A minus projection of B over A, this vector dot A. Okay, so what is the projection? If you remember the formula, projection of B over A is a scalar times A. What is the scalar? Scalar is A dot B over length of A squared dot vector A. So this is a number because dot product is a number, length is a number, so I have a number times A. That's the projection. So I'm gonna keep writing B dot A minus, I'm gonna replace the formula in here, the scalar times A and dot A. Okay, so this is a number. This is a number in here. A dot A would be the magnitude of A square. Remember the formula. Okay, so on the denominator, I have magnitude of A square, and then I have on the numerator, I have magnitude of A square. So they would be canceled. But let me just rewrite that. So these two would be canceled because they're just numbers. And I get what? I get B minus A, B dot A minus A dot B. And as you know, in the dot product, we can change the order. So these two vectors, they are the same vectors. So the answer would be yes. Therefore, A dot the orthogonal projection is 0, meaning that they are orthogonal to each other. In the figure below, if U is a unit vector, find U dot V and U dot W. We have a triangle in here, and since these sides, they have equal length, this is an equilateral triangle. Equilateral triangle, which means that all the angles, including this one, are 60 degrees. So for finding U dot V, I can use the geometric definition of the dot product. So let me give you a recall. If we have two vectors like this, the vector A and the vector B, then A dot B would be the length of A, the length of B, and the cosine of the angle between them, this angle. So now I have U dot V, which would be the length of U, the length of V, and cosine of theta, and theta here, the angle between these two is pi over 3. The length, since U is a unit vector, and since V and U have the same length, this is also 1, and cosine of pi over 3 is 1/2. So the dot product between U and V is 1/2. How about U and W? So to find this, I need to have, as you see in the recall, I need to have both A and B starts at one point. W is like this, so I can move U to here. You see, vectors can move, okay? And now the angle between these two is here. What is this? The whole angle here is 180 degrees, or this is pi. This part is 60. So this part is 120 degree. Or I can say that this is pi minus pi over 3. It's good because I can write U dot W then. It would be the length of U, the length of W, and cosine of 120, which would be pi minus pi over 3. This is 1, this is 1. How about this one? Let me give you one more recall for the unit vectors. Okay, so if we have a unit circle, this is pi over 3, and pi minus pi over 3 would be here. Okay, so the whole thing here is pi minus pi over 3, and to find the cosine, as you see, this is the cosine axis, and as you see that the cosine of pi minus pi over 3 is on the negative side. So this is equal to negative cosine of pi over 3, which would be negative 1/2. So the answer here is 1 times 1 times negative 1/2, which would be negative 1/2. I would like to find a unit vector that is orthogonal to both I plus j and I plus k. Okay, so let V be the vector that I'm looking for. V1, V2, and V3 are its coordinates. I know that V dot I plus j is 0. Why? It's just because V is orthogonal to that, which means that the dot product is 0. Okay, so what is I plus j? I plus j, let me write I. I is 1, 0, 0, plus j is 0, 1, 0. So I plus j is 1, 1, 0. Therefore, I have V1, V2, V3, dot product with 1, 1, 0, and I get V1 times 1 plus V2 times 1 plus V3 times 0. So I get this one equals to 0. What is I plus k? I is 1, 0, 0. K is 0, 0, 1. So this is 1, 0, 1. I know that V times I plus k is also 0 because V is orthogonal to that. So I'm going to have the same thing, V1, V2, and V3 dot with 1, 0, 1. It's equal to V1 plus V3, and it's equal to 0. Okay, well, what else do I know? I know that v is a unit vector, which means that the length of v is 1. What is the formula for length? Is the square root of the first coordinate square, second coordinate square, and third coordinate square. This is equal to 1. So let me square both sides. So I get v1 square plus v2 square plus v3 square is equal to 1. So as you see, I have 3 equations in here. One is this one. The second one is v1 plus v3 equals to 0. And this is the third one. So I have a system of equations that I need to solve. Okay, so v1 plus v2 equals to 0. v1 plus v3 equals to 0, and v1 square, v2 square, and v3 square is equal to 0. Okay, look at this one. I need to solve this one to find v1, v2, and v3, right? So v2 is negative v1. For the second equation, I get v3 equals to negative v1. And now I have all my variables in terms of v1. So I'm gonna substitute v2 and v3 in this equation for the last one. So I'm gonna keep v1 square. Instead of v2, I'm gonna write negative v1. Negative v1 square. And then instead of v3, I have negative v1. And, oops, not 0, it should be 1. This is my third equation, right? It should be 1. So, what do I have? I have v1 squared plus negative v1 squared. Here, it's just v1 squared and v1 squared. So, I have 3 v1 squared equal to 1. So v1 squared equals to 1/3. So v1 is 1 over square root of 3 plus minus. So v1 can be 1 over square root of 3 and can be negative 1 over square root of 3. Okay, so if v1 is 1 over root 3, then v2 is the negative of v1. So v2 would be negative of that. And v3, based on this equation, is negative of this. Okay? So together, my vector v would be 1 over root 3, negative 1 over root 3, and negative 1 over root 3. Okay? With the same reasoning, since v1 is negative 1 over root 3, v2 is the negative of that. So v2 would be positive 1 over root 3, and I have this v. Great, I found 2 v's, both of them are acceptable, and both of them are unit vectors that are orthogonal to these 2 vectors. Why did I get 2? It's just because one of them is in this direction, the other one is in the opposite direction. But both of them are orthogonal to 2 given vectors.